Hello all, welcome back to Climate Dynamics. Today in Lecture 4A, we'll be reviewing some concepts from atmospheric dynamics that will be necessary as we continue to explore convection in the atmosphere. The reference for this material is Marshall and Plum, Chapter 3.2 and 3.3. In this section, we're going to learn definitions of hydrostatic balance, scale height, Lagrangian frame, Eulerian frame, material derivative, adiabatic motion, potential temperature, lapse rate dry adiabatic, saturated lapse rate, and Foehn wind. The first concept that we're going to be touching on is hydrostatic balance in the atmosphere. Under the parcel dynamics model, individual air parcels are characterized by various thermodynamic properties, in this case density, pressure, and temperature. These three are related via the ideal gas law that we have discussed previously. Further, the chemical composition of these parcels is determined by its constituent mixing ratios, which are typically denoted by Q sub I. Finally, the parcel property of velocity is also captured. Hydrostatic balance is the primary force balance model that's used to explain the vertical structure of the atmosphere. In general, observations indicate that vertical velocities are typically small in the atmosphere, especially when averaged over very large scales. So in our parcel model, we're going to investigate how the atmosphere would be structured under this simplification. For the parcel model, we're going to assume that the parcel has a mass given by capital M, which is equal to density times the cross-sectional area times the height of the parcel, and it's going to be experiencing a pressure force on both the top face and the bottom face. On the bottom face, it's going to be experiencing a total pressure force equal to pressure times the cross-sectional area, and on the top it's going to be equal to pressure plus some delta pressure times the cross-sectional area. Note that in the atmosphere, pressure typically decays with height, so delta P here is nominally negative. When vertical velocity is approximately zero, these density and pressure end up being functionally related to one another. So if the cylinder of air is not accelerating, it must be subject to zero net force. What are the forces that are acting upon this parcel? Well, we have the two pressure forces, one at the top and one at the bottom, but we also have gravitational force. The gravitational force experienced by the fluid parcel is equal to the gravitational acceleration, lowercase g, times the mass of that fluid parcel. Plugging that in, we get a gravitational force equal to negative g rho delta A delta z. We say that a fluid is in hydrostatic balance when external forces, here gravity, are balanced by the pressure gradient force. If we sum up these three forces and force them to equate to zero, we then find, through some simple mathematical manipulation, that we get delta P plus g times rho times delta z must equal zero. Using a Taylor series expansion, we can approximate delta P as di P di z times delta z, and plugging that in then gives our approximation for hydrostatic balance. Thus, for hydrostatic balance, it must be that pressure and density are related to each other through this simple relationship, di P di z plus rho g equals zero. In combination with the ideal gas law, which relates density, pressure, and temperature, hydrostatic balance actually enables all the thermodynamic variables to be specified purely in terms of the vertical temperature profile and a single constant associated with surface pressure. If we can also further manipulate this hydrostatic balance equation by integrating it from the top of the atmosphere downwards, noting that the pressure, as z goes to infinity, is equal to zero. Taking this integral then gives us an equation for the surface pressure, because we can use fundamental theorem of calculus in order to replace this derivative with the value of the pressure at the two endpoints of the integral. Proceeding with this manipulation, one finds that the surface pressure is directly proportional to the total mass of the atmosphere above it. This is one way, then, in order to use the surface pressure measurement in order to estimate the total mass of the atmosphere. Again, we can use ideal gas law in order to reduce the hydrostatic balance equation to a functional relation between pressure and the vertical temperature profile. Taking the ideal gas law and plugging it into the hydrostatic balance equation then gives us this expression di P di z plus Pg over RT equals zero. Thus, if temperature is specified, we can exactly integrate this equation. A common approximation that is used for the atmosphere is the isothermal approximation, where we say that the atmosphere maintains a constant temperature throughout its height. This is of course not true in practice. As we saw last lecture, the temperature of the atmosphere actually behaves fairly linearly in the troposphere. And as we investigate convection further, we'll actually consider this case as well. But an isothermal atmosphere provides a shockingly close approximation to reality. So plugging in a constant temperature profile and integrating this equation then gives us a simple differential equation, dp di z equals negative p over h, where h is defined as the scale height, or the isothermal scale height of the atmosphere. It is equal to r T naught over g, where r here is the specific gas constant for dry air. Integrating this then gives pressure as a function of altitude is equal to the surface pressure times an exponentially decaying profile that is simply scaled by the scale height of the atmosphere. Alright, let's see how well this works in practice. We already know that the troposphere varies fairly linearly with height, but it turns out that if one chose 273 as your constant isothermal temperature, you would get a scale height of approximately 8 kilometers. Plotting this vertical pressure profile on a log plot here on the right-hand side versus the actual observed pressure shows that the isothermal profile actually provides a fairly decent approximation to the actual pressure up to an altitude of about 7 or 8 kilometers. Above this, there is a clear divergence between the two, but note that the errors are fairly small because this is a logarithmic scale. The scale height of the atmosphere is more concisely and formally defined as the altitude gain needed for the pressure to decay by a factor of E. If we consider the whole atmospheric profile, one can use a scale height of approximately 6.8 kilometers. This arises from an isothermal temperature of 232 degrees Kelvin. Under this approximation, we see that, for the most part, the isothermal approximation matches fairly well with the observed pressure profile, with only small deviations because of the cooler temperatures in the troposphere, the warmer temperatures in the stratosphere, and cooler temperatures within the mesosphere. Alright, now that we've reviewed hydrostatic balance, let's move on to discussions of material derivative. So, the material derivative concerns how we describe and quantify properties of the global atmosphere. One can think of the atmosphere in many different ways. The way that we've been thinking so far involves tracking singular fluid parcels in terms of position, as well as their thermodynamic and dynamic properties. So how do we quantify these properties, and how do we relate positional measurements, such as at a single point, to the behavior of fluid parcels as they move through the atmosphere? The Lagrangian frame is primarily what we've been investigating so far. This is where properties of the whole atmosphere are described in terms of individual fluid parcels and how those parcels move around. In the Lagrangian frame, there are many properties that are invariant to transport, things like mixing ratio, specific humidity, and parcel mass. Because the parcel itself can deform, but basically maintains the exact same molecular composition, you get conservation of mass as you follow the fluid parcel. An example of a measurement in the Lagrangian frame, or a quantity that has been measured in the Lagrangian frame, are quantities taken from weather balloons. In the weather balloon context, the weather balloon is being pushed around by the air and taking measurements as it floats around. Thus, it is following the flow of the atmospheric fluid being passively transported by the background wind field. Also, the weather balloons are basically isolated fluid parcels. Although there is some leakage of mass from inside the weather balloon to the outside, one nonetheless has to a large degree containment of the molecules that were in the weather balloon initially. The Eulerian frame is this alternative way of measuring the atmosphere. In this context, we consider a single point and measure the atmosphere over a long time period. In the Eulerian frame, the properties of the whole atmosphere are described in terms of individual measurements taken at fixed locations over time. An example of a way of measuring the atmosphere in the Eulerian frame is through weather stations. Here, for instance, we see measurements of local wind speed, we see measurements of temperature, as well as barometric pressure. Typically, these weather stations are placed in fixed locations and observe the properties of fluid parcels as they pass by. The Eulerian frame can also be used to depict quantities on a map. If we take every point at which we have a measurement and we lay that out on a grid, one can then get a snapshot over the grid of a particular field. In this case, this Eulerian map is showing the warmest day of the year from 1981 to 2010 accumulated from various measurements plotted on a gridded field. So, why are we considering two frames of reference? We know that the same physical principles must hold regardless of the reference frame used. That is, we still have conservation of mass, conservation of energy, conservation of momentum, but multiple reference frames are useful for evoking different understanding of how the atmosphere behaves. That is, certain concepts can be more easily explained in the Lagrangian frame, hence why we've spent quite a bit of time investigating individual fluid parcels and investigating how they behave in response to external forces. Whereas other quantities, such as the warmest day of the year map that I showed previously, can provide more context and information on a grid. But there is nonetheless a relationship that we can evoke in order to connect these two frames. Specifically, we're interested in connecting them via the material derivative, which allows us to equate time rate of change in the Lagrangian frame with time rate of change in the Eulerian frame. Formally, the material derivative describes the time rate of change of some physical quantity of some material element, for instance a fluid parcel, that is subject to a velocity field. It is denoted usually by this capital D notation, that is capital D over capital DT. Quantities, then, that are subject to the material derivative are written, for instance, as capital dq over capital dt. A quantity that is conserved has zero material derivative following a fluid parcel. All right, in order to understand how these two frames are equated, let's consider a parcel that has some property of the atmosphere, such as temperature, that moves some distance in some time delta t. We're going to consider the initial time to be t naught and the final time to be t sub 1. Over the time period, here it has moved a distance delta x and a distance delta y in the zonal and meridional direction. The difference in temperature between these two locations is denoted by delta capital T. So we would like to calculate the change in temperature over this time delta t following the parcel. In order to do so, we can use a Taylor series expansion in order to expand the temperature around the initial position. What we find is that the total change in temperature, delta capital T, can then be related to each of the individual dimensions, the three spatial dimensions and the temporal dimension, along with higher order terms. However, since we'll be considering the limit of small time and small spatial displacement, all these high order terms can be neglected for the time being. If we assume that these delta t are small, that is, we can ignore these higher order terms. All right, so we're going to take this formula, we're going to divide through by the difference in time, delta small t. This then produces a formula which looks very similar to a chain rule type expansion of the temperature field. However, let's explore what each of these terms means. On the far left-hand side here of the second equation line, what we see is the change in temperature divided by the change in time, but this quantity refers to the change following the fluid parcel. On the right-hand side, the very first term we see is the Eulerian rate of change of the temperature. That is, it's taken at a fixed position in space. Analogously, these other derivative terms of the temperature field are also taken at a fixed position in space. The deltas, the uppercase deltas here, refer to quantities that are measured along the flow of the fluid parcel, that is, within the Lagrangian frame. So if we take the limit then for small delta time, what we then can do is replace these capital deltas then with the capital D's and replace those ratios with material derivatives. So remember by definition that the change in the zonal position with respect to time following the fluid parcel is simply equal to the zonal velocity of that fluid parcel. That is, if you're moving a certain zonal distance in a certain amount of time, this is simply basically distance over time and hence corresponds to a velocity of that fluid parcel. analogously for meridional distance as well as vertical distance. So, replacing those material derivatives with the velocity components, one then obtains this expression that then relates the Lagrangian frame change in time to the Eulerian frame change in time of temperature, as well as a term that is associated with change due to advection. So to review, the left-hand side here represents the Lagrangian frame, temperature following the fluid parcel, and the right-hand side represents the Eulerian frame, measurements taken at a point. Thus, this formula connects the Lagrangian frame and the Eulerian frame. Alright, so let's go back and review. The Eulerian frame is a measurement taken at a point. Here I've rearranged the formula from the previous slide so that the advection term is now moved to the right-hand side along with the Lagrangian change of temperature. The Eulerian frame time rate of change then can be related to the Lagrangian rate of change via this formula. The Lagrangian frame denotes the temperature change following that fluid parcel, so as it's advected across the map. A question one might have then is, why is this advective term negative in this expression? So this is the same as taking the derivative of temperature along this line of traversal of the fluid parcel and multiplying by -1. So why the -1? Well, let's depict this as a one-dimensional plot. We're going to define a new coordinate starting from just before the initiation of the fluid parcel's movement and ending simply just after the conclusion of that fluid parcel's movement. If you take the temperature along that curve and plot it now on the right-hand side as a relationship between the independent quantity S and the dependent quantity T, one finds that if you have an increase in temperature along that line, and you have advection of temperature, one would expect that the cold temperatures would be moving upstream, that is, moving towards larger values of S. So, if you have a positive U, you have a positive gradient here, which is di-T di-S, one would expect that you get colder temperatures at the location denoted by the house over time. Hence why the negative sign needs to be present within the derivative. Okay, let's go and discuss adiabatic transport now. So recall back to the first law of thermodynamics, which relates the change in internal energy within a fluid parcel to heating and work that is done. The internal energy can be related to the change in temperature of that fluid parcel via the specific heat capacity at constant volume times the change in temperature. The work done on a fluid parcel must be associated with a change in volume of that fluid parcel, and so it can be written as -P times d alpha, where alpha here is the specific volume, that is, volume per unit mass. In fact, this is simply the reciprocal of the density. Plugging these two in, one then obtains the first form of the thermodynamic equation, which includes our standard thermodynamic quantities of temperature, pressure, and density, and relates that to diabatic heating and cooling, which is additional heat added to the system. One can further manipulate this equation by plugging in the ideal gas law. This allows us to then replace the alpha term with pressure and temperature, and thus expanding this gives an equation analogous to the one shown on the bottom. The CV plus RD term can be combined then in order to produce the constant of heat capacity at constant pressure. This then leads to the second form of the thermodynamics equation, which relates terms associated with change in temperature at constant pressure, and a second term that includes work done to change the pressure of the fluid. Note that this is not the same dW term that showed up in the first form of the thermodynamic equation, because some of that has now contributed towards the change of pressure of the fluid. So this is represented in what is known as a differential form. That is, it relates infinitesimal changes in temperature and pressure to one another via this diabatic heating term. So if we consider small fluid parcel movements in the context of quasi-static equilibrium, we can then take these terms as representing the change in the thermodynamic properties of a fluid parcel as it moves through the Lagrangian frame. Thus, we replace these differentials with material derivative terms. So now we obtain essentially the same equation, except here being in a much more useful form for analyzing atmospheric behavior. On the right-hand side, because we've divided through by our time rate of change, we need to replace the heating term with a heating rate, which has units of joules per kilogram per second. All right, for most large-scale motions, the amount of latent heating in clouds and precipitation is relatively small, and initially we're going to focus on the case of purely dry dynamics where one doesn't need to consider the heating that may be incurred because of condensation or evaporation of water. So in the absence of such sources and sinks of energy, one has J equals 0, that is, we have no diabatic heating, and entropy of the fluid is conserved following the motion. The motion of fluid parcels, in the absence of these external sources and sinks of energy, is referred to as adiabatic motion. So adiabatic motion is particularly relevant for large-scale vertical motion and in the analysis of atmospheric stability. This is actually the type of motion that is analyzed almost exclusively in the Introduction to Atmospheric Dynamics class that is featured alongside these lectures. If you need to review adiabatic motion, I suggest you go back to the Introduction to Atmospheric Dynamics lectures and watch some of those videos. All right, so we can manipulate this thermodynamic equation further in order to get it into an even more useful form. Again, using ideal gas law, one can plug this into the second form of the thermodynamic equation for atmospheric fluid parcels and perform some manipulations. First of all, we're going to plug in the ideal gas law and divide through by temperature. This then allows us to combine the terms associated with temperature and the terms associated with pressure. By writing these terms as 1 over temperature times the material derivative of temperature with respect to time, and 1 over pressure times the material derivative of pressure with respect to time, we can actually combine this into a single term that is a material derivative of a logarithm. Recall that the derivative of a logarithm is equal to 1 over the contents of the logarithm times the derivative of the interior of the logarithm. Here I've introduced T0 and P0, which are arbitrary constants that allow the quantity within the logarithm to remain free of units. When one then performs some further manipulations, taking Cp and R to be constants, one can actually combine these material derivative terms into a single quantity. Here we have the time rate of change following a fluid parcel of log of, within the square brackets, capital T over T0 times P0 over P to the R over Cp is equal to the heating rate divided by Cpt. So this quantity within the logarithm is referred to as the potential temperature. This is also referred to as Poisson's equation in some of the literature. In particular, this quantity theta, known as potential temperature, is equal to temperature times P0 over P to the R over Cp, where R here is the dry specific gas constant. So plugging this into our equation on the top, we get a very simplified form. Material derivative of the logarithm of theta divided by T0 is equal to J over Cpt. So we basically have the change in potential temperature within the fluid is related to the diabatic heating term. If the flow is adiabatic and the diabatic heating term is actually equal to 0, then the T0 can be neglected, and we basically end up with simply that the time rate of change of potential temperature following the fluid parcel is equal to 0. Specifically, this means that the potential temperature is conserved following an adiabatic flow. All right, the quantity P0 typically represents sea level pressure. In that case, potential temperature then has an alternative definition, which is the temperature that an air parcel would have with initial temperature T and pressure P if it were adiabatically brought down to sea level pressure, or in this case, the reference pressure 10 to the 5 pascals or 1,000 hectopascals. Potential temperature is closely associated with entropy of the fluid. Specifically, if potential temperature is conserved, we have no external heating or cooling of the fluid parcel, and so we basically end up maintaining entropy of the fluid. Thus, constant potential temperature is the same as constant entropy. All right, here's a question for you to test yourself. If the temperature at the top of the continental divide is negative 10 degrees Celsius, or 263 degrees Kelvin, and the pressure is 600 hectopascals, the ideal gas constant for dry air is 287 joules per kilogram Kelvin, and the specific heat capacity at constant pressure is 1004 joules per kilogram Kelvin. Can you calculate the potential temperature at the continental divide? And can you calculate the temperature a dry air parcel would have if it sinks to the plains at a pressure level of about 850 hectopascal with no external heating? Be super careful in doing this calculation and make sure that your units are consistent when you do these manipulations. In particular, pressure has to match the units of pressure that you use need to match the units of P naught as well. And the temperature in this expression must always be represented in Kelvin. All right, we can now use this notion of potential temperature in order to investigate the expected lapse rate of the fluid through the troposphere. Below the tropopause, the atmosphere cools roughly linearly with altitude. This feature is governed by adiabatic motion and the thermodynamics of air parcels as they are lifted and subside. The magnitude of this decrease of temperature with height is formally referred to as the lapse rate. For a well-mixed, dry adiabatic, hydrostatically balanced atmosphere, the potential temperature tends to not vary in the vertical direction. That is, as long as it's well mixed, your potential temperature change in the vertical tends to be effectively zero. So, in a dry adiabatic hydrostatic atmosphere, we know that the temperature must decrease with height. The question is, how quickly does this temperature decrease? Note that this is primarily a feature of compressible fluids, such as the atmosphere. For incompressible fluids, a different strategy is needed in order to understand changes in vertical temperature. After some mathematical manipulation, it can be shown that the potential temperature satisfies the first equation on this slide, namely temperature divided by potential temperature times the derivative of potential temperature with height has to equal dT dI z plus G over Cp. Recall that we said for a well-mixed vertical atmospheric profile, we have di theta di z equal 0. So plugging in 0 on the left-hand side allows us to solve for di t di z. The lapse rate, again, is the rate of cooling of the atmosphere with respect to height. And for this case, one can show that negative di t di z then must equal G over Cp. This quantity is then equal to 9.8 Kelvin per kilometer, or 0.0098 Kelvin per meter. This is formally known as the dry adiabatic lapse rate. The reason being that it's the rate of change of temperature of a fluid if potential temperature is conserved and there are no additional diabatic sources of energy, including condensation or evaporation. So in adiabatic motion, with no external sources of heating, if a parcel moves up or down, its temperature will change. Specifically, it will change at this dry adiabatic lapse rate as it moves up and down. Note that adiabatic does not mean isothermal. This is often a point of confusion that comes up whenever I'm teaching this class. Isothermal is very different than adiabatic for compressible fluids. In fact, we see that adiabatic here means that the temperature changes linearly with height. Adiabatic refers to the fact that there is no external heating or cooling. So what is going on here is as the parcel rises, its pressure is also decreasing. Consequently, as the pressure decreases, you have a decrease in temperature of the fluid as well. All right, let's consider this applied to a particular scenario of incoming dry air on the left-hand side as it encounters some topographic variation such as a hill or a mountainside. In this case, this could refer to, for instance, wind coming in off of the Pacific Ocean as it encounters the coastal range or as it encounters the Sierra Nevadas. The initial temperature of this air is T naught. As that air rises over the hill, again, it's being forced by dynamics as the fluid comes in and thus is able to rise. It experiences a dry adiabatic lapse rate, and so by the time it reaches the top of the hill, the temperature is then lower than the initial temperature T naught. As the air parcel descends on the other side, it warms. As long as the pressure on the other side of the hill is the same as the pressure on the incident side of the hill, that is, as long as the windward and leewards have the same pressure, one will find that air parcels on the leeward and windward side will have approximately the same temperature as well. That is, this is a reversible process. On both sides, the lapse rate is effectively constant. That is, it is the dry adiabatic lapse rate of 9.8 Kelvin per kilometer. The dry air that then exits will have temperature T0 as well. Let's consider now the diabatic case. This, of course, is closer to the real world. In the real world, the troposphere does contain moisture, and as you lift air parcels that contain moisture, there is a potential chance that condensation will occur. If condensation does occur, that is, if the vapor pressure within the fluid reaches the saturation vapor pressure given to us by the Clausius-Clapeyron relationship, then condensation will occur and you will have diabatic warming of the fluid associated with that condensation. So if it were the case that dry adiabatic motion governed the troposphere, one would find that the lapse rate should be about 9.8 K per kilometer. However, referring to the International Standard Atmosphere, which is basically a lookup table for various thermodynamic quantities related to the atmosphere as a function of altitude, one finds that they actually adopt a standard constant lapse rate of 6.5 K per kilometer throughout the troposphere. This is because this value actually matches much closer to observations. So why do we have a lower lapse rate than the dry adiabatic lapse rate? The answer is pretty simple. The atmosphere is not dry. Motion is not dry adiabatic. If air reaches saturation and the conditions are right for cloud formation, namely as long as we have cloud condensation nuclei present, then vapor will condense to liquid or solid and release energy in the process. So in general, for any sort of moist fluid parcel, we will have J not equal to 0. This then requires a concept known as the saturated adiabatic lapse rate. The saturated adiabatic lapse rate is formally the rate at which air cools with height when the air parcel is fully saturated. This is approximately 5 K per kilometer, but is dependent on the air temperature. Specifically, this lapse rate takes into account the fact that condensation has a net warming effect on the fluid parcel. That is, as air condenses and produces water droplets, it's extracting the coldest water molecules from the substance and putting that into liquid water. Consequently, the air that is remaining tends to be warmer than a dry adiabatic air parcel would be. However, the global atmosphere is also not completely saturated everywhere. That is, we are not at 100% relative humidity at all times. And so the actual lapse rate is actually closer to 6.5 K per kilometer. Hence, this is the quantity that is adopted by the International Standard Atmosphere. So let's return to our previous problem of incident air coming upon some topographic variation such as a hill or coastal range. Here we're going to assume that the air, though, is saturated, which is not a bad assumption for air that is coming directly off the Pacific Ocean. The air, again, has temperature T0. As the air is pushed up and over the mountain, it again cools, except this time it is now cooling at the saturated adiabatic lapse rate, the SALR. Nonetheless, its temperature when it reaches the peak is still going to be less than the temperature of the incident air. However, in this case, the temperature will be warmer than the dry adiabatic case because condensation of moisture is leading to diabatic warming of that air parcel. Now, when the air descends on the other side of the mountain, it is not undergoing condensation and it's not undergoing evaporation. That is, the moisture that has been squeezed out in the form of liquid water has already rained out on the windward side of the mountain. So, as it descends, it is actually going to be experiencing the dry adiabatic lapse rate. So, the winds that then emerge on the leeward side of the mountain are warm winds, and in particular, the winds that are produced in this manner are commonly referred to as Foehn winds. Here, the temperature on the other side is actually going to be larger than the incident temperature. Formally, a Foehn wind is a dry, warm, downslope wind that occurs along the lee downward side of the mountain range, and it arises naturally from an understanding of moist thermodynamics of air parcels. Alright, that's all for the dynamics review from this lecture. We'll continue next time exploring dry convection and then exploring moist convection. Thank you.